So we are going to start a new topic today, which is actually called Newton's laws. Sometimes this topic is also called dynamics. Okay, dynamics. Whatever we studied previously was called kinematics. So in dynamics, we investigate the cause of motion. Okay, so here we investigate the cause of motion. In fact, what causes motion? If a particle is at rest, what makes it move? In fact, the answer to this question is what is called force. We introduce a new quantity called force. So defined simplistically, force is basically a push or a pull on a particle. Who is pushing? Someone. It may be you or any other object or any other entity, or a pull. In fact, a better definition of force, force is defined as force is an interaction, interaction between two bodies. So interaction between two bodies. See the word two. It's not a single body. It is an interaction between two bodies. This is very important. So for there to be force, there must be two bodies, or at least two bodies. There can be more, but there must be at least two bodies for there to be a force. Now, there are different types of forces which we encounter, but all these forces can be classified or categorized into four major categories. So we have four major categories of forces. So all the forces fall into one of these four categories. First, we have what is called strong force. Strong force. I'll come to this, what it means. Second, we have electromagnetic forces. Electromagnetic forces. Third, we have what is called weak forces. Weak. And the last of all is what we call as gravitational force. Gravitational force. In fact, the order in which I have written, it is the descending order of strength. So maximum strength is for strong forces, and gravitational force is the weakest of all forces. It is very surprising to note that we feel gravity is strong, but soon we are going to see that gravity is the weakest of all these forces. In fact, gravity is weaker than weak forces. So any force that you see falls into these categories. The forces which keeps protons in an atom together, or protons and neutrons in an atom together, that is called strong force. Generally two protons which have positive charges repel, but something keeps them together. So that is strong force. So it is more powerful than the force of repulsion between protons. So it is strongest of all forces. The next is electromagnetic. Most of the forces that we encounter fall into this category, electromagnetic forces. The repulsion between protons is also electromagnetic. In fact, sometimes we call it electrostatic, and we are going to learn about that in second year or later, at a later stage in my lectures. We are going to learn about that. Then there is weak force. This is something which was discovered in the late 60s. I believe in the late 60s. So when cosmic rays come from the outer space and fall on Earth, there are certain particles which are reaching Earth. They are called mesons. This mass of meson, I believe, is neither so large as that of a proton, nor too less than like an electron. It is somewhere in between. The mass of this Particularly we have mu mesons. Sometimes it is called muon. It is neither between, the mass is between a proton and an electron. So when these interact with matter, some forces result, which are called weak forces. Well, this is something which even I do not know to a great extent. So, but still, we call them weak forces when mesons interact with matter. And last is gravitational force, and we have a special topic called gravitation, where we will study about this force in great detail. Okay, where we will study about gravitational force in great detail. So most of the forces that we see, for example a push or a pull or friction or tension, whatever forces that we study, they fall for our purpose only into two categories, either electromagnetic or gravitational. Okay, in this course, in my lectures, we will very rarely deal with the strong force, or what is called nuclear force. Strong force is also called nuclear force. So we will very rarely deal with that, only maybe towards the end of this course. And we almost never deal with these weak forces. Okay, we never deal with them. So we never deal with this weak force in our course. Now let's discuss some of the forces which we are going to encounter in this. So first we are going to discuss about gravitational force. Okay, I am going to discuss only very briefly about each of these. So gravitational force. See, any two objects in the universe which have mass attract each other. This is the law of nature. So if I have, for instance, two particles, this is particle A, this is particle B. What's a particle? Something whose size is 0, but that can have mass. So if mass of this particle is m1 and this is m2, then these two particles attract each other. Anything that has mass attracts every other object which has mass. Okay, so m1 will pull m2, so there is a force on m2 in that direction, and there is a force on m1 in this direction. So m1 pulls m2, m2 pulls m1. You see, it is interaction between two bodies. This force, any force is interaction between two bodies. There must be two bodies. Okay, now in fact we will study later that this force of attraction, the force with which m1 pulls m2 or m2 pulls m1, is given by F equal to G m1 m2 by d square. Okay, the force depends on both the masses, product of both the masses. It is inversely proportional to square of distance between them, which means if distance increases, force decreases very quickly. Okay, now this brings up a question. If every two bodies attract each other, then if I am sitting in a classroom, I must attract the table. Then why doesn't the table move? My answer to that question is, well, I attract the table, but the ceiling attracts the table, the fan attracts the table, you attract the table, a nearby table attracts the table, the blackboard attracts the table. So where will it move? All these are exerting force. The net force adds up to 0. The total force adds up to 0. So things which we see are stationary because the total force due to all the objects is 0. On the other hand, if I take this table into space and there is nobody else, then the table gets pulled towards me. I also go towards the table. Both attract each other. In space there are no other objects apart from myself and the table. Okay, so any two objects which have mass attract each other with a force which is given by product of masses and inversely proportional to square of distance between them. Okay, this is gravitational force. Typically what we are going to study is the attraction due to earth. So if we have earth, okay, and if we have some body of mass m which is very close to surface of the earth, when I say very close, this height is negligible compared to radius of the earth. That height is very small compared to radius of the earth. So if radius of the earth is 6400 kilometers, this height is 1 meter or 2 meters. So it is almost zero. The body is very close to the surface of the earth. In that case, force on the body is given by G, mass of the earth, mass of the body by the radius square, gmm by r square. Here I am taking the distance between the center of the earth and the body. And in fact, if you substitute the value of G, the value of radius of the earth and the value of mass of the earth, it turns out to be 9.8. And this is what I call as G. So mg is the force with which earth attracts a body of mass m. If I keep here another body of mass capital M, the force of attraction will be capital Mg. This force of attraction is always towards center of the earth. Okay, so earth attracts every object towards its center. So it is attracting me with a force, and that force is my mass into G, my mass into 9.8. So this mass into G, mg, this is the force with which earth attracts. It is also called weight. Okay, so weight is nothing but the force with which earth attracts a particular object. That is called weight of the object. So weight means force. Mass is not force. Mass is the amount of matter present in the object. Okay, amount of matter. So I cannot define actually exactly what is mass. It's a fundamental quantity. Mass is a scalar, whereas weight is nothing but force, which is a vector quantity. Force is a vector quantity. Okay, weight is a vector quantity, mass is a scalar quantity. Weight could be zero. For example, in outer space, there is no acceleration due to gravity because of earth. So weight is zero. But mass can never be zero if there is some matter. Okay. Of course, here we are not going into relativity. There is a concept in relativity that mass changes with speed, and rest mass of photon is zero and so on. Anyway, we are not into relativity. So generally, if you have an object, we take its mass to be a constant. It does not change unless you break the object or change the matter contained in the object. Okay, so this is all about gravity. So earth attracts every object with a force which is called weight of the object. It is given by m into g, mass of the object into g. The g value generally is 9.8 meter per second square. This g is also called acceleration due to gravity. We saw this even in projectile motion. Okay, sometimes we take the value of g as 10 for convenience, but unless otherwise stated, you must take g value as 9.8. You cannot take it as 10. Okay, now this is the first force which we have seen. This force falls under the category of gravitational force only. It is gravitational force only. Now let's see the next force which we encounter very frequently in our discussion, and that is normal contact force. The name itself says something. Normal. Normal is a term which is sometimes also called perpendicular. For example, if somebody says draw a normal to the curve, draw a perpendicular to the curve at that point. Normal, perpendicular, both are same. Contact force. So this force comes into picture only when two bodies are in contact. First of all, there must be two bodies. Only then there will be a force. So the two bodies must be in contact. Only then this force can occur. But remember, just if they are in contact, also this force may be zero. They must deform each other. They must press against each other. Two bodies, when they press or when they compress each other, when they deform each other, then there is this normal contact force. For example, if I have one block here, if I have another block here, I push this block this way with 1 Newton. I also push this block with 1 Newton. Now both the blocks are pressing each other. They are compressing each other. So there should be a normal contact force. How it will be? It will be perpendicular. Normal means perpendicular. Perpendicular to contact surface. What is the contact surface here? That is the contact surface. So it will be perpendicular to that line. So on the left block, that force acts this way. On the right block, the force acts that way. Okay. So if the left block pushes the right block with 10 Newton, the right block also pushes the left block with 10 Newton. You see, this force is coming into picture because both these blocks are in contact. That's why it's called contact force. And normal means it is perpendicular to contact surface. The violet line shows the contact surface. It is perpendicular to that, this way and that way. It is acting on both the blocks. So if one block pushes the other block, the other will push the first block. Normal contact force. Okay. Now for example, if I have a step and there is a stick like this, okay, so on the stick there is a normal contact force. Suppose if I redraw the stick, there is a normal contact force that way. It is perpendicular to this contact surface. It is in that direction. There is also a normal contact force on the step. Okay, there is one normal contact force on the stick. So the step exerts a force on the stick. The stick also exerts a force on the step. We will see more about this in Newton's third law. Okay, force exerted by two objects on each other, we call them action-reaction pair, but we will see that in Newton's third law. So wherever there is some contact with compression or with deformation, there will be normal contact force. On the other hand, if I just keep two blocks in contact like that, I don't apply any force like what I have shown here, then normal contact force between these blocks is zero. They don't press each other, they are just in contact. They do not compress each other, they do not deform each other, they are just in contact. So normal contact force between these blocks will be zero. Okay, only when they deform each other there will be normal contact force. Then there is another type of force which is tangential contact force. Tangential contact force, which we also call as friction. The force which occurs between two bodies in contact due to their relative motion or due to their tendency of relative motion is called friction. So when two bodies which are in contact try to move in such a way that there is relative motion between them. Relative motion means, for example, if there are two blocks like this, if this is moving with 2 meters per second, if this also moves with 2, there is no relative motion. But if it moves with 3, then they rub each other. So there is tangential contact force which is called friction. Okay, so in this case friction acts on the upper block also, friction acts on the lower block also. When you rub your two hands, frictional force acts on both of your palms, both of your hands. Okay, so it is a tangential contact force. Okay, the force is parallel to this contact surface. It is in that direction. That is the contact surface and it is parallel to that direction. That's why it's called tangential. Perpendicular to contact surface, for example, that line is called normal. Okay, that is normal. Maybe I should that is normal. I'll draw a clear picture. So that is normal. So tangential contact force or friction is also very important. In fact, we will study about friction in great detail as we proceed further along with these lectures. Then there is what is called a tension. Okay, tension in a string. Generally we speak of tension either in a rod or in a string. Okay, it is force exerted by a string on an object because of the stiffness in the string. So tension is equal to the magnitude of force which a string exerts on a block or object, okay, due to the stiffness of string. So because the string is stiff, it pulls a block or any object attached to it. The force with which the string pulls is called tension. Okay, for example, I have a block here tied by a string and I am holding it. The block does not fall down even though earth is exerting certain force on the block, mg. Okay, why it is not falling down? Because the string is exerting a force on the block. Okay, the magnitude of this force which the string exerts on the block, that we denote it as tension. It is because the string is stiff. Okay, it is pulling the block, countering mg. Okay, that force is called tension. For example, I can tie a string to a wall and pull the string. Okay, so the string exerts a force on the wall whose magnitude is tension. Of course, when I pull the string also pulls me. For example, if this is my hand, string is also pulling me. So because the string is tight, it pulls the wall towards itself, which is to the right, and it pulls me towards itself, which is to the left. You see, the same string is pulling the wall to the right, but it is pulling me to the left because I am exerting a force on the string. Okay, is that clear? So tension will only pull an object towards itself. It can never push. For instance, if I have a block, okay, if I connect a string and with the help of string if I try to push the block, I cannot, because the string is loose or slack. String is slack here. String is slack. So I cannot push the block, but I can pull it. So if I have a string which is tight, if I have two blocks connected to it, remember the string is tight. So string is pulling the right block to the left, it is pulling the left block to the right. String can only pull, it cannot push. Okay, this is most important. So the force with which the string pulls an object is called tension. And later we are going to see more details about this tension. Okay, generally when the string is massless, tension throughout the string remains the same. But if the string has mass, tension throughout the string will not be same. Okay, we are going to see more about this later. More detailed explanation. Now, apart from this, we also encounter in many problems what is called a spring. So we must discuss the force exerted, okay, by a spring. It's also called spring force. Okay, spring force. Now, a spring will exert force only when it is expanded or compressed from its original length. So let us say I have a spring of certain original length L0. Suppose I expand this to a new length L0 plus x. Then the force exerted by the spring is given by k into x, where k is a constant known as spring constant. So you see, the force exerted by a spring depends on this quantity x, which is the expansion in the spring. This x is expansion of the spring. So this expansion is nothing but final length minus natural length, new length minus natural length. Natural length of the spring is L0. The new length of the spring is L0 plus x. So this change in length Okay, this expansion is called expansion. It could be compression also. If x is negative, if final length is less than initial length, then the spring is getting compressed. So x is either expansion or compression of the spring. Okay, generally it is called displacement. Why? Because the spring is connected to some body, maybe a block. So if spring expands by some amount, the block connected to the spring also moves by same amount. Okay, so it is called displacement. Okay, when a block moves from one position to another position, we call it displacement of the block. So x is nothing but the displacement of the block connected to the spring, or sometimes we say displacement of the spring. Okay, so force exerted by a spring depends on this displacement. More is the displacement of the spring, more is the expansion of the spring, more is the force exerted by the spring. So it's not a constant force whatever spring exerts. Okay, the force exerted by spring is variable force. Okay, force exerted by a spring is a variable force. Okay, it's not a constant force. So this force depends on the expansion x, or force is proportional to the expansion x, or we write F is equal to kx. You also put a minus sign here sometimes. F is minus kx, because this force exerted by the spring is opposite to displacement. For example, if I have a spring here tied to a wall and I connect it to a block, okay, if I pull the block to the right, spring expands and it exerts a force on the block to the left, is it not? So if displacement is to the right, force is to the left. On the other hand, if I compress the block, I push the block to the left. Okay, I push the block to the left. So if displacement is to the left, spring will push the block to the right. Force is to the right. So force is always opposite to displacement. Okay, force is always opposite to displacement when you are changing the length of a spring from its original length. So when you are expanding or compressing a spring, force exerted by the spring is opposite to displacement. This opposite nature is shown by the minus sign here. So the minus sign tells you that this force and displacement are in opposite directions when you are either compressing or expanding the spring. Okay, and this constant, as we saw, it is called spring constant. Spring constant. Okay, the units of the spring constant are Newton per meter. Force is measured in Newton. Okay, so K is given by minus F by x. Force is measured in newtons. X, or displacement, is measured in meter. So that's the unit of spring constant. Now this spring constant, what does it tell us? It tells us something about the strength of the spring. For example, if spring constant is too high, the spring is very strong. For example, the spring between two railway compartments, okay, which prevents these two railway compartments from coming closer to each other when brakes are applied. That's a very strong spring. The spring of the shock absorbers of your bike, that's also a reasonably strong spring. The spring in your ball pen is not a very strong one. It's a weak spring. If you pull it to a great length, the spring nature will be destroyed. Okay. So if spring constant is huge, if it has a high value, that's a very strong spring. If spring constant has a lower value, it's a very weak spring. So for example, you can have spring constant as 100 Newton per meter. You can have 10,000 Newton per meter. So this is a very strong spring. This is a strong spring. This is a very weak spring. Okay, that's the idea. Now, why is that? Why, if K is more, the spring is strong spring? Okay, see, if K is more, For example, let us say it is 1000. Then if I pull x by 1 meter, if x is displacement of the spring is 1 meter, okay, if x is 1 meter, force will be minus 1000 into 1 or 1000 newtons. On the other hand, if spring constant is only 100, F will be minus 100 into 1 or only 100 newtons. So I am pulling the spring in both the cases by 1 meter. In this case also I am pulling it by 1 meter. Okay, in this case also I am pulling it by 1 meter. So for the same displacement of the spring, the force is more when K is 1000. The force is less when K is 100. Okay, so if you pull two springs by same amount, the one which exerts more force is a very powerful, strong spring. The one which exerts less force is a weak spring. Okay, so this variation of spring force with displacement is very important. Okay, spring force is not constant. The more you pull the spring, the more the force it exerts. You take shock absorber of the bike, try to pull it. The harder you try to pull it, the more the force it will exert. Okay, the more it expands, the more the force spring exerts. The more it compresses, the more the force spring exerts. Okay, if you compress by 1 meter, the force exerted by spring is 1000. If you compress by 2 meters, force exerted by spring will be 2000 more. Spring force is not a constant. Spring force is a variable force. So spring force, okay, is a variable force. This is a very important statement. Okay, so we have seen all these forces, mainly gravity, tension, normal force, spring force, friction, and so on. There may be other forces which are between two charges, let us say, which we call as electrostatic force, or force on one charge due to a moving charge, which could be a magnetic force, and so on. Okay, but we will take them as we go to those respective topics. So now I want to get to Newton's laws, which is what I will do in the next session. Okay, we discussed something about these forces. Force is nothing but a push or pull, or a better definition of force is it is interaction between two bodies. There must be two bodies for there to be a force. Okay, for example, I pull a block. The two bodies here are I and the block. Earth attracts moon. The two bodies here are earth and moon. So there must be two bodies for there to be a force. It's a very important statement. Okay, we will see Newton's third law, the significance of this statement. The statement that there must be two bodies for there to be a force. Okay, so in the next session I am going to introduce the three laws, Newton's laws, which revolutionized the way we think now. All the modern developments are based on these laws. Okay, so we are going to see those three laws in the next session, and then we will see how to apply these laws to many problems. Okay, thank you.